Welcome back to Neural Intel, everyone. Let's dive right into it. Today, we're looking at training large language models, LLMs as they're better known these days, more specifically, how to train them efficiently, and some really cool new research that was presented at EMNLP last year in 2024.
You got it. It really is fascinating stuff. Getting these massive models to actually work well
Right.
involves figuring out what training data to use. This can be a real drain on computing power if you're not careful.
Right. The normal way of optimizing these things, like deciding which data sets to use and how much of each to feed an LLM, has usually involved a brute force kind of approach.
Hmm.
You try different combinations of how much weight to give each data set, train the model from scratch over and over again, evaluate how it's doing, and it just takes forever. Not to mention all the computing power you need for each of those training runs.
Yeah, that's the main problem with the usual approach. It just takes so long. Techniques like grid search look at loads of different mixes for your training data. Eventually, you'll find something that works, but as you add more data sets, it gets really complex. It really slows you down. So much computation just gets eaten up by the whole process.
Yeah.
And once you've trained the model with that specific data, changing anything is a huge pain.
So that's where the research from Amazon Science that we're looking at today comes in. What they're doing is training separate models on individual data sets and then looking at how to combine those models to get the best results. It's a totally different way of thinking about it, isn't it?
Absolutely. That's why their approach, which they call distribution edited models, DEMS, was recognized at EMNLP.
Uh-oh.
It's so efficient in terms of how it models, trains, and even lets you make inferences. How it actually uses the models is the main innovation.
Okay, well, let's get into the details then. How does it actually work? You mentioned distribution vectors. What are those?
Okay, so you begin with a large language model, one that's already been pre-trained, like a base or foundation model that has a good general understanding of language.
Yeah.
Then you fine-tune that model. So you're taking all that general language knowledge and applying it to specific tasks.
Okay.
Now, here's the key part. For each of these new fine-tuned models, the researchers subtract the structure of the original model, the parameter values, which are like millions or billions of tiny settings.
Right.
These get changed during training to help the model learn. What you get when you do this subtraction is what they call the distribution vector. It shows you what changes happened in the model because it learned from that particular data set.
That's amazing. It's like isolating the impact of each data set. So now you have these learning fingerprints for each data set. What do you do with them to make the final DEM?
So you take the pre-trained model and add back in a weighted combination of these distribution vectors.
Okay.
The big question then is, what are the best weights to use so that the final model works well across a whole range of tasks?
And this is where the big efficiency gain comes in, right? They're not messing around with the original data mixes.
Right.
How do they actually find those weights for the distribution vectors?
So they use something called perplexity, but it's used a bit differently here. You measure the perplexity of each of those fine-tuned models against another data set, a validation data set.
Hmm.
What it means is that the lower the perplexity is, the more that model has learned specifically from its training data. The more distinct its signature is, the less predictable it is.
So a fine-tuned model that's really learned the specifics of its data will have a low perplexity compared to that original general model.
Yeah, exactly. And this is what makes it so efficient. You only need to run the validation data through each fine-tuned model once to figure this out. This is so much faster than having to train and evaluate tons of different models. This optimization process is amazingly streamlined.
So the DEM approach is built on two big observations, right?
Yes. The first is that by training the models individually, you can make sure each model captures all the little details and patterns from that data. If you just mixed all the data together, you'd lose some of that.
Oh, okay.
And the second is this efficiency gain. Using perplexity is such a fast and effective way to find the right combination of those learned signatures.
Yeah. Better models and you need less computation.
Exactly.
Okay, so let's go through all the steps in this approach. I think there are 5 main ones.
You got it. The first step is what they call individual distribution training. You take your pre-trained model and you fine-tune it on each of your data sets, one at a time.
Okay.
You save the model after it's been trained on each data set.
Right, so step 2 is where you calculate those distribution vectors we were talking about.
Exactly. For each of those fine-tuned models, you find the difference between its parameter values and the parameter values of the original model. That difference tells you what that data set taught the model. Step 3 is all about figuring out how to combine those vectors, what they call optimization of merging coefficients.
Right.
So here's where you use that perplexity idea. The researchers look at different combinations of weights for the vectors,
Hmm.
and they can quickly calculate the perplexity for each combination. They then choose the weights that give the lowest perplexity on that validation dataset.
So that's the best way to combine the learning from all the data sets. And then step 4 is actually putting them all together.
Right, that's merging of distribution vectors.
Oh.
You take those weights you just found and do a weighted sum of the vectors. Then you add that sum back to the parameters of the original pre-trained model,
Cool.
and you have your final model. It's ready to use on all sorts of different tasks.
Really amazing. And the last step tells us about some of the advantages of this approach.
Yeah, it's really flexible because you've got all these separate components, the distribution vectors.
Right.
If you want to include another data set, you just train a new model on it, calculate its distribution vector, and add it to your DEM. You don't need to retrain everything from scratch, which makes it super adaptable and scalable. That's so important because the real world throws you curveballs, and your data is always changing.
So how did the researchers show that this works in practice?
So they used it to instruction tune some large language models,
Okay.
and they tested it on models ranging in size from 3 billion parameters all the way up to 13 billion.
Wow.
And the results were incredible. They were able to reduce the training cost by up to 91% compared to the old way of doing things.
91%. That's huge.
It is, right. And that's just the reduction in the amount of computation. They also saw improvements in performance, up to 16.1% on some of the benchmarks they used.
So not only is it super efficient, but it actually gives you better models.
Exactly.
What kind of benchmarks did they use?
Well, they used established benchmarks like MMLU, BBH, and HALM to measure the overall capabilities of the models, but they also tested them on data sets that require specific types of reasoning, things like MathQA for solving math problems, supernatural instructions, which covers a wide variety of instruction types, and chain of thought data, which is used to train models to think step by step. The fact that DEM did so well across all these different areas is pretty impressive.
So it's really flexible, and it wasn't just limited to one specific model size, right?
Right. The benefits, both the reduced training cost and the improved performance, were seen in all the different model sizes they tested, 3 billion, 7 billion, and 13 billion parameters. That scalability is key to making this work in the real world.
So just to sum up, we've got models that perform better than traditionally trained models. They're effective on all sorts of different tasks. The approach works with models of different sizes. And most importantly, it needs a lot less computing power.
Right. It's tackling some of the biggest problems in the field.
This research really shows how innovation can lead to amazing progress. To reduce the training costs so much and get better models at the same time is a phenomenal achievement.
And the way it works is so elegant, isolating what each data set teaches the model into these vectors and then using perplexity to combine them is such a clever and effective solution.
Totally.
The researchers have published a paper on this, DEM Distribution Edited Model for Training with Mixed Data Distributions. It was presented at EMNLP in 2024. We'll put a link to it in the show notes.
Awesome.
Think about what this kind of efficiency could mean for the whole field. If training LLMs becomes a lot easier, who knows what kind of amazing research we'll see.
Yeah, it could open so many doors. It's exciting to think about.
It is.
Thanks for joining me for this deep dive into distribution edited models. We'll see you next time for another look at the latest in AI research.
See you then.